Two massive naval warships are locked on a direct collision course. Neither captain wants to sink, but yielding means surrendering a highly contested tactical position. This physical standoff scales perfectly to the geopolitical brinkmanship of the nuclear age. During the Cuban Missile Crisis, the US and Soviet Union steered their military apparatuses toward a mutual catastrophe, waiting to see who would flinch first. The philosopher Bertrand Russell observed that eminent statesmen managing global survival had adopted the exact mechanics of a reckless teenage dare. They were playing chicken. The structure of chicken contains a severe paradox. Both players share the identical primary goal of avoiding mutual destruction. Yet, because the victor is the one who refuses to yield, pride and strategic advantage incentivize both players to feign total irrationality. You win by convincing your opponent you are crazy enough to actually crash. Game theory attempts to mathematically solve this standoff to predict who will swerve. But when the models assume complete information, where both players know exactly what the other values and fears, the mathematics break down. When two perfectly rational actors possess transparent knowledge of each other's breaking points, the attempt to predict the outcome results in a theoretical impossibility. This diagram shows a side-by-side comparison of two classical models of conflict: the stag hunt, a coordination game, and the game of chicken, an anti-coordination game. The stag hunt operates on strategic complements. A strategic complement is a condition where a player's incentive to escalate their aggression increases if they believe their opponent will also escalate. The math rewards matching the opponent's intensity. The game of chicken operates on strategic substitutes. A strategic substitute is a condition where the incentive to escalate actually decreases as the opponent's aggression increases. In chicken, the math rewards doing the exact opposite of whatever your opponent does. This graph maps the optimal responses for both players to locate the Nash equilibria. A Nash equilibrium is a stable state in a game where neither player can gain an advantage by unilaterally changing their own strategy. Look at the reaction lines for chicken. They cross at 2 points. The math produces two equally valid, diametrically opposed outcomes. Player A swerves while player B drives straight, or player B swerves while player A drives straight. Classical game theory fails to predict human conflict because it assumes a fantasy. It relies on the premise that adversaries have perfect, transparent knowledge of each other's payoffs. In reality, enemies never know exactly what the other is willing to lose. To resolve this mathematical deadlock, economists Sandeep Baliga and Tomas Sjostrom proposed injecting a dose of reality into the model: payoff uncertainty. You do not know exactly what your opponent values. This is a continuous horizontal number line representing the hostility parameter. The hostility parameter is a private, quantified value that dictates an individual player's true internal willingness to engage in conflict. At the extremes of this spectrum, we find rigid behavior. On the far left are dominant strategy doves, who will always choose peace regardless of the cost. On the far right are dominant strategy hawks, who will always choose war, even if it ensures mutual destruction. The vast majority of players fall into the middle zone. These are the moderates. Their actions are not predetermined. Instead, they must calculate their moves entirely based on their beliefs about their opponent's level of hostility. This calculation generates a cutoff strategy. A cutoff strategy is a mathematical threshold a moderate player sets, choosing aggression only if their private internal hostility exceeds that specific point on the line. Private uncertainty, the fact that you cannot know exactly where your opponent's cutoff lies, forces players into a unique, rational strategy that breaks the classical deadlock. We can observe how this works by applying the cutoff model to a game of strategic complements, like the stag hunt, where the underlying dynamic is a mutual lack of trust. The trigger for conflict begins at the edge of the spectrum. The mere existence of dominant hawks on the far right creates a baseline level of anxiety for the moderate players, located right next to them. The moderates closest to the edge realize they cannot risk playing dove against a potential dominant hawk. Out of sheer self-preservation, these almost hawks are forced to adopt a hawk strategy. This initial defensive shift changes the probability math for the next tier of moderates. Now facing an expanded pool of hawks, they too must shift to a hawk strategy to protect themselves. This stepwise mathematical cascade is called the iterated deletion of dominated strategies, progressively eliminating options that yield lower payoffs regardless of what the opponent does. This phenomenon is a spiral of fear. Anticipated aggression feeds on itself sequentially across the spectrum until it hits a rigid equilibrium cutoff. In environments governed by strategic complements, uncertainty acts as an accelerant. It systematically converts moderate self-preservation into unavoidable conflict. Now we shift focus to the game of chicken. Because chicken is a game of strategic substitutes, the overarching goal for a moderate player is to intentionally mismatch their opponent's move. Here, the existence of dominant hawks on the spectrum impacts a completely different demographic. It triggers the weakest moderates near the center left, rather than the strongest moderates on the right. Fearful of a catastrophic crash with a dominant hawk, the weakest moderates proactively choose to back down and play dove. This is the deterrence effect in action. This triggers an inverse reaction. Observing a high probability of capitulation from the left side of the spectrum, the strongest moderates are mathematically emboldened to play hawk. They push forward because they know the opponent is highly likely to yield. This is the spiral of deterrence. The fear of extreme conflict forces the weak to yield, which logically and rationally justifies the aggression of the strong. In a game of chicken, uncertainty does not breed a runaway escalation of fear. Instead, it enforces a strict hierarchy where predictable capitulation stabilizes the entire system. All of this relies on an assumption about how player types are distributed. What happens if players draw their hostility levels from a shared, highly correlated environment, like two generals trained in the exact same military academy? These two probability distribution curves show the difference between independent types, which have broad, unpredictable variations, and correlated types, where variations are highly concentrated and predictable. In a stag hunt, a tight correlation guarantees a unique equilibrium. It accelerates the fear spiral, because assuming the enemy thinks exactly like you logically justifies your own defensive aggression. But this exact same correlation destroys the mathematical uniqueness of the chicken game. Moderates in chicken want to mismatch their opponent. If a moderate believes the opponent is highly correlated to their type, they cannot predict who will yield. The system breaks down into multiple equilibria. For a game of brinkmanship to find a stable resolution, adversaries cannot be too similar. There must be a vast, unpredictable wilderness of idiosyncratic uncertainty between them. If the uncertainty isn't independent enough to force a resolution, the math of chicken requires one final condition: ex ante asymmetry. Ex ante asymmetry is a pre-existing, measurable imbalance in baseline hostility before the game even begins. A publicly known imbalance, say one player being historically more aggressive, skews the cutoff calculations for both players before they ever make a move. The outcome of this imbalance is absolute. The weaker player's mathematical best response becomes preemptive capitulation, granting the stronger player unchallenged dominance without a fight. The classical view of brinksmanship as a test of irrational willpower is a fiction. Who swerves on the collision course is not decided in the frantic final moments of a crisis. It is predetermined by the underlying architecture of their private uncertainties and structural imbalances. In the highest stakes conflicts, perfect transparency guarantees a fatal deadlock. It is the shadows of incomplete information, the specific things we do not know about our enemy, that mathematically engineer our survival.